Okay, we are going to get into example 9.15. It states a common scuba tank is an aluminum cylinder that weighs 31.7 pounds empty. When full of compressed air, the internal pressure is between 2,500 and 3,000 psi. Suppose such a tank, which has been sitting motionless, suddenly explodes into 3 pieces. The first piece, weighing about 10 pounds, shoots off horizontally at 235 miles per hour. The second piece, 7 pounds, shoots off at 172 miles per hour, also in the horizontal plane, but at an angle of 19 degrees to the first piece. What is the mass and velocity of the third piece? So notice it says initial velocity, but we're really looking at final velocity. So I'm just going to say velocity of the third piece, okay? And instead of doing a bunch of unit conversions, I'm just going off the textbook here. They went ahead and did it for us, okay? As you can see, we've got our unit conversions, pounds to kilograms, and then miles per hour, all the way to meters per second. Okay, so I just wanted to say that. This is our initial mass, so I'm just going to say M. And then we have our first piece. I'm going to say that's M1. Okay. And then our second piece, 7 pounds, that's going to be M2. Okay. Then we have our velocities. So this velocity here was of our first piece. So I'm going to say this is V1. And then my second piece down here is going to be V2. Whoops, V2. Okay. So the first step is to find our mass of that third piece, and they went ahead and did it for us, but I want to explain what they did. So they have their initial mass, or their total mass, I would say, is M. So that is here. So this is their total mass, and minus our other mass. So we have M1 and M2. And so that should equal M3. And that's really just because M, or our total mass, is equal to M1 plus M2 plus M3, right? It's just that they changed it around so that they can solve for their third mass. So this is M3, okay? All right, with all of that initial stuff beside, let's start analyzing this problem. So we had an initial scuba tank, and it went through an explosion. Okay, so again, explosion is when we have one piece of something and it explodes into multiple pieces. Okay, so this is a graph of what it looks like after the explosion. So we had some tank and then it went off into these different directions. Okay, all right, so your book does it a little bit differently how I'm going to do it. I'm going to do it how we just did our last example so that we stay consistent in our methods. They do it a little bit differently. It shouldn't matter in the end. We should get the same answers. Okay? All right. So first things first, we need to find our initial momentum in our x-axis and in our y-axis, and then set those equal to our final momentums in the x and the y-axes. Okay, so I'm going to write those down. So we have P, I'm going to say P initial, comma, x, and we're going to set that equal to P final, comma, x. Okay, so that's going to be our first thing. Second thing is P initial, comma, y equals P final, comma, y. Okay? So I'm going to work with the first one. So this is going to be my first step, is looking at all the equations. So initially, our tank was motionless. So we didn't have any initial velocity. So our initial momentum would be mv sub I would just be 0 then, okay? Since our velocity was 0, okay? All right, so then we're going to set that equal to our final momentum, which will have P1, right? Which is going to purely be in the x direction. You know what? I am going to just write down P1 for now. Okay. And then we'll have P2. Now P2 is a little bit different. So we have P2. It has an x and a y component to it. Okay. So think of this as a right triangle quickly. Okay, and we want this x-axis. We know that angle theta, okay, so it's going to be what? Adjacent over hypotenuse, right? Okay, so that means it will be cosine of theta, where theta is our 19 degrees. I'm just going to write that over here. All right, so we have our partially of our x-axis completed. Now we need our P3. Okay, P3, we don't know what it is. We don't know what direction it's going to be in. So we can say P3. Okay, we'll have some kind of x component. Okay, then we have our y, and this is going to be the same over here on the initial, because we don't have any motion. So it's motionless. It has a 0 velocity. Okay. Then we have P1, and there's no y component to it, so that's just 0. Okay. Now looking at P2, we do have a y component, so we have P2 times, and again using trigonometry, we say opposite over hypotenuse. So now we have sine theta, okay, plus, again, P3, which we don't know, okay. Okay, so from these now we want to solve for our P3, and in terms our velocity in these directions. So I'm going to go ahead and rewrite this now as m1 v1 plus m2 v2 cosine theta plus m3 v3 comma x. Okay, because I don't know exactly what that's going to be yet. I don't know if there's some angle here. There might be. And so we'll have to figure that out. Okay, and we will. So now we're looking at the y. We have m2v2 sine theta plus m3v3 comma y. Okay, so this is our setup. We then want to solve for our v3x and our v3y. Okay, so I'm going to start that on the next page. So from 1, I'm going to say, I'm going to solve for v3x. Okay, so solve for v3x. We have v3 comma x is equal to m1v1 plus m2v2 cosine theta all over m3. Let me double check that, make sure that's correct. Yes, okay. And so we can go ahead and find this now. So let's see, our m1 M1 is 4.5 kilograms times V1, which is 105 meters per second, plus our second mass, which is 3.2 kilograms, times our velocity in the second here is 77 meters per second. Whoops, wrong way. 77 meters per second times cosine of 19 degrees over M3, which we solved for earlier as 6.7 kilograms. Okay, so we can plug that into our calculators and we'll get what? So 4.5 times 105 plus 3.2 times 77 times cosine of 19 divided by 6.7. Oops, I didn't do that right. There we go. Is that right? That could be right. Okay, so this actually gets 105 meters per second. I'm going to double check my work on that just to be safe. Let's see, cosine 19 plus 4.5 times 105. Yeah, okay. I just wanted to double check. And then for the second equation, we'll again solve for V3 and Y component now. So V3 comma Y is going to be M2 V2 sine of theta, over M3. Okay, so we'll say this is going to be 3.2 kilograms times 77 meters per second times sine of 19 degrees over 6.7 kilograms. So 3.2 times 77 times sine 19 divided by 6.7, and we get 12.0 meters per second, and that's in the Y direction. Okay, so now if we want to solve for the overall V3, we'll have V3 comma x squared plus V3 comma y squared, square root that. So we'll have 105 squared plus 12.0 squared, square rooted. Let's go ahead and do that. 12 squared. And we get V3 is equal to 106 meters per second. So now this is my velocity of that third part. Okay, now if I want to find the direction, I'm going to have to solve this equation, tan inverse v sub y over v sub x. So we have tan inverse of v sub y, or v3 sub y, I'm sorry, is 12. So we have 12 meters per second over v sub x, which is 105 meters per second. Okay, and then so we'll have, let's see, tan inverse of 12 over 105. We get this small angle of 6.52 degrees. Okay, so phi is equal to 6.52 degrees. Okay, give me just a moment. Oh, we'll start on the next video. Sorry about that.